Hello. So today I had some time again, and I was working on how to create a FIFO queue that's backed by the disk. And although there's already a in-memory queue library called DQ, it seems to work well enough. I might be able to come up with something faster, but for this project, I really want to start to work on getting things out relatively quickly and maybe taking a few shortcuts if there are some. And so using a library that may not be the most efficient is good enough for me. I briefly considered using mmap for this type of thing, and I came to the conclusion that it would be a lot of work, and again, I don't want to spend too much time on this project. So let's see. What I decided to do for the disk portion of it is, let's say that we have the memory queue, and we realize, oh, it's kind of too big. So then we want to take some off and put into the file system. So what we do is we start to write to a file. We'll call it file.1, and then later on, let's say that the memory queue becomes too small, and we want to fill it up from the disk. So then we start to read from F1. Then if it becomes too big again, we will start to write. As long as we didn't fill, so if we have F1 here, and as long as we didn't read all the data, so there's still some left, then we'd start at F2 for the new write. And so that once the read gets done with F1, then it would go ahead and start on F2, and we'd push any new writes to F3, and so on and so on. One of the reasons I'm doing this way is because if I try to do it all in one file, it ends up, I think I explained this last time, that you end up having to do basically memory management in a file, which is kind of stupid. So if I started to, let's see, write here and say I got up to here, actually maybe start this over. Let's say I had a disk file and I wrote here, and then I started to read, let's say up to this point. I have a decision now. I could either go back here and start to write, or I could continue my writes here. And in either case, it's no good. If I go back here and write again, I might reach this limit here, and then what do? I have to move to another spot to continue writing. If on the other hand, I get to here, or I'm here, and I start to read, and I just continue to write, all this space becomes kind of like unused disk space. So as you can see, you start making these gaps, and so that's why I need to have more than one file to make that simple. So there's that. There's the other thing is that this disk FIFO queue needs to be persistent, so it needs to have an operation to save everything to disk, and do it in an atomic way, so that if let's say that it's working and then the system crashes, it can go back to the previous state of the queue, where it was last committed. So let's say that we have F1 and we have F2. What I do, that's a strange way to write it, I guess, F2. What I do is I'm going to create an index file, which is basically just going to have an at 1 and 2. And when this gets written out, or move, basically there's going to be a move operation, which moves are atomic, so that they're good for trying to commit things, because they only either happen or don't. So basically what I do is create an index.temp, and then once I've completed it, I move it to index, and then that becomes the current journal. So what happens, actually before all this happens, is that we have the memory queue, and we just dump everything out, we write everything out to the disk. After we've done that, then we create this temp index file, and then we move it into index. And like I said, index is going to contain 1 to 2, which says, in this particular example, that says that the committed journal starts on file 1 and ends on file 2. Now, when we load back up again, we'll take f .1 and f2 and add them into like a list, which the read thread will use. So the read thread's going to have this one and this one to read through before it goes on to F3, right? And so what happens then, and also what happens is when we write, we create a new file to write to F3. So as long as we're writing to new files, which we are, we're just going to start, when we write, we're going to start to write it to F3. F1 and F2 are untouched, and there's still the index out there, which contains 1 and 2. So if the system crashes, when we load back up, we know, oh, the index contains 1 and 2, therefore any file beyond it is garbage and we can delete it. So that's how we keep the committed journal from being, basically keep the committed journal around to prevent it from being destroyed when we go ahead and process more items. Okay, so then what happens is after this step, let's say we want to create a new journal. One thing I forgot is, in addition to 1, they also have the position, the read position in the first file. So let's say that we want to like commit a new journal. So what we do, let's say this is not destroyed, and we've gone this far with our reads. So what we do then is we create a new index, which contains 2, and also contains this position here, and contains 3, which is the ending file. And this is the starting file and the position where we actually start. And then what we would do is, so then after that we go and we would delete all the files that are in the old index. Well, first we commit this. So first we have index temp, and then we move this to index proper, and so it contains 2 in the position and 3. Then we go ahead and we delete F1, the old index file. And that's how we recommit after we committed previously. So yeah, that's what I did with that. I'm just working on how to structure the code right now. And yeah, it was, I went through several different ideas, and this is what I came up with. So the end is kind of simple, but the process was a little complex. All right, talk to you later.